Okay. I didn't write the put a note. Okay. Wait. I'm getting quite a number of inquiries about the lab report. There's a mistake here. By right, it's due on week 7, but the date here wrong. All right. So it's actually due on Monday of next week. All right. But if you see the problem, all right. But since it's my mistake, so if you want to hand up a bit later, it's okay. But quiet please. But the way I scheduled it is I wanted to give you 2 weeks in between the lab reports. All right. So if you delay this one, then the next one is week 9. All right. So I only give you 1 week. All right. And so on and so forth. You delay this, it goes into the end of the semester already. Okay. So the structure as planned, hopefully the date's not wrong. All right, is for them to be due in 2 weekly intervals. All right, including this one with semester break. All right, so that you can. Right. Okay. The impact jet one. Yes, only one. I progressively the flow measurement week 9, flow visualization week 10. There's a semester break in between, and then the pipe flow one at the end of week 12. All right. So if you, I think I think this date is a bit late because you won't have any time to do the next report. So if you want to hand in early next week, okay, but sometime next week. Right? Not until the following Monday, because then we'll give you very little time to do the flow measurement report. All right? So it's actually in week 7. So these are the deliverables in week 7, the mistakes on the date. So sometime in week 7 you should hand in. Is that okay? All right? Is that okay? Okay. All right. So preferably by the end of the week, so that at least you give yourself a bit more time to work on this one. If not, you get very close. All right. Okay. So next one is okay. Okay, settle down, please. All right. All right, so today we have a new topic. All right. This. All right. I know tomorrow holiday and day very long for some of you. Yeah, very long. What to do? I didn't fix your timetable. Okay, so we don't need to do this. All right, if not, we'll run behind the schedule. Okay. So please sit down, keep quiet. It's very noisy in front here. Okay, now you settle down here now. Okay. All right. So this topic is all right. Up till now, things very it's simple enough, not? Up to now, things pretty simple, right? Okay, pretty simple. Yes or no? No. Okay, they're pretty, you can do them analytical, you can get some solution out already. Alright, more or less. Okay, not simple lah. I already tried to digest most of it so that it's fairly straightforward for you guys. Not simple enough. Alright, so okay, so this part here, okay, so we can call it theoretical also lah. The next half of the course, there are some things that are not so not so straightforward. All right, there could be complex things happening. All right, like turbulent flow. All right, pump performance. That kind of things. All right. So we need a tool. We need a tool that can be used to predict these type of things based on not necessarily just theoretical calculation or estimation, but maybe from previous. So we need a tool. Okay, tool. Predictive tool. You are engineers, you need to know predictive tool. Okay, so that we can use not only theoretical theoretical analysis, but maybe experimental results or correlations. All right, this mainly either from experimental or simulations. Okay. Okay, but the number of parameters is normally very big. All right, a lot of parameters. Okay, and everything depends on everything, so it's very complicated. So we want a tool that simplifies things a bit. Okay, and this is what we are doing here. Okay, so this is the dimensional analysis exercise. Okay, so I mean some examples. Okay, all right. Complex things like flow past aeroplanes, all right, flow past automobiles, all right, flow inside turbo machinery like pumps, turbines, and so on. Flow inside piping networks and so on. Quite complicated. All right, cannot simply analyze using Bernoulli. Correct? Cannot assume no losses. There is losses. Cannot just analyze using momentum and so on. So there's a lot of other more processes happening. Some we do understand, some we don't understand, but we want to, based on experimental findings, come up with some sort of, all right, most likely you don't have to. Earlier people will have come up with some sort of observation. They'll compile their results. Okay, now when we learn a little bit here, we will hopefully can be able to decipher their results. Okay. So that we can use those to predict. Okay, so later on there will be like example. Yeah, put them. Okay, example is I think I put in the lab folder. All right, example is there's like chart like this. Okay, this is a Moody chart. You see here, they plot Reynolds number, they plot friction factor. You have absolutely no idea what that is. Never mind. Okay, and you got all these lines here. This is basically for turbulent pipe flow, the losses. Okay, someone earlier has done a lot of experimental work. I compiled it all into this graph here. Okay, for all the different configurations that you could possibly dream of. With this, after you learn this topic, and then after that pipe flow, you should be able to decipher what hopefully you know what the Reynolds number is by then, and then be able to calculate that for your particular problem, and therefore use this graph as a predictive tool to, in your case, my pipe diameter is a fixed this size, I have this long, and so on. What sort of pressure drop can I estimate? All right, based on this graph. Does that make sense? All right. So this is a tool that can summarize or condense the data. All right, because if without this, got so many parameters: pipe length, pipe diameter, pressure drop, velocity, what other things that could be in the pipe, the roughness, and so on. So many different parameters. All right. So this is a tool to condense it all into one graph. Okay. So based on this graph, hopefully by the end of this course, okay, you will be able to, given any arbitrary pipe configuration, be able to calculate the pressure drop, all right, or the pressure or the losses in the pipe, all right. So that this tool, this dimensional analysis, basically, what should I say? Okay, basically allows you, all right, to either, in the case where that data is not available, produce data that is a bit more universal beyond your experimental rig, and if data is available, to use that data to predict whatever is going to happen in your particular case. Does that make sense? A little bit? No. All right. If no, then this is the more easy way to this is another. I'll explain it in another way. All right. The other way is, okay. The what I just explained to you is a bit more universal. All right. If you want to be more specific, then let's be more specific. Okay. More specific is, let's say you have a particular problem. All right. Wind blow past a bridge. Okay. This bridge is in Japan. Longest span means longest part between the two things is over 2 kilometers. All right. Japan wind very strong. I think even now wind very strong. Okay. So before they build the bridge, they need to make sure that the bridge won't fall down. Right. The wind won't blow it down. All right. For example, all right. But there's no way to build the bridge first and then test. Okay. That's too big a risk. Okay. Build the bridge down and then observe, it's too big a risk. So there must be a way to study it. Okay. You can only do so much with analytical tools. You will either have to do simulations, numerical simulations, or experimental testing. But again, there's no way to build a full-scale one to test, because that would be, that's already building the full scale. All right, that's already building the bridge to test. Okay, so example also could, in this case, is a bridge. Example could also be like a process plant, since a lot of chemical engineering students here. So process plant, you wouldn't build a big one to test. Okay, process doesn't work. Boss not going to be very happy. You already invested all the land, all the piping, all the equipment. Okay, and things don't quite really work. Okay, so you build a small one. So in chemical engineering, I think they call pilot plant. All right. So you need a way to test. Okay, you test your pilot plant, but you need to make sure your pilot or your model actually behaves like full scale. All right. So this tool will also ensure that scaling between model and full scale. It's not, in this case, it's not only important to just get the geometry right, to scale down the geometry, right? Like you see the die-cast model 1 to 20. Okay, as long as you do it the 1 to 20, everything look right. No, it's not enough. Okay, there are a lot of other parameters to consider. Okay, for example, in this case, all the dynamic aspects, like the weights. All right, that's why they add weights here, because the actual cable is a lot heavier than the cable that they use, so they have to simulate that. The bridge deck, the stiffness of the bridge deck, and so on. Okay, they simulate up to 90 meters per second. 90 meters per second, how fast? Cannot be, is it? That's over 700 kilometers. No, it must be 90 kilometers an hour. All right. Sometimes strong winds can go over 100 kilometers an hour. All right. By this, it can't be 90 meters per second. 100-ish in the 100 to 200 kilometer range is quite does occur in some, maybe not in Malaysia, but in some places where they do experience strong winds. Okay. So they have the bridge actually, because it's a cable span bridge, it actually deflects quite a lot. Okay. So this is the tool. Okay. Number one, to scale between model and full scale. Number two, in certain cases where the problem is very common, like pipe flow, we can compile all the results, all right, hopefully, and then you can just use that rather than having to do model. Every time you want to study pressure drop in your big pipe, you have to go build a small pipe, measure it there, and then scale it up. Then no need. You can already done all the experiments, compile all that data into a chart or plot or graph, and then use that to predict. Okay? Does that make sense now? So there are two ways. One is just a one-to-one study. One is if it's a very common problem like pipe flow or some heat transfer or some other type of problem like that. Okay? There will be no point you building a rig to do the same thing. People already done it. So you compile the results you can use. So that's those are what called correlations. All right? Those are normally either from experimental and lately maybe some simulations they can get those type of data which you can use. So you don't need to go and do it again. All right. So in this case, these slides come from Clayton. This one's stuck. Oh. Okay. So they do a lot of wind tunnel testing. So it's a bit the example there is a bit slanted that way, but it could be for other applications too. This picture just because you not only need to, because the bridge takes about 2 or 3 years to build. All right. So during that time, you're in the various stages of construction. Every year the strong wind will come. Just because you're halfway built, you need to make sure that your bridge will still stand so that you can continue building. All right. You build halfway and then strong wind comes and it doesn't stand, also it's a problem. Certain places have very tall buildings. Okay. So this Taipei 101. All right. Okay, so again, they'll need to do testing. All right. This one, because each building, the architect, the geometry is unique. All right. The terrain is unique. So you cannot just look it up in a book. All right, of compiled results, what the performance of that building is. So each one is unique. So and you cannot be building it and then test. So you do wind tunnel model testing. All right. Model testing. So that's the model. Okay. So I think this is a building in Melbourne, and then this is the actual one. Maybe graphic artist impression, and this is the one in the model. Okay. I think they test a few others and so on. Okay. This is a road, bridge deck. Okay. They also test for aeroplanes, right? Early wind tunnels were pretty primitive. Okay. I'll skip all this. All right. So, so it is important. All right. Not only for the geometry to look the same. All right. The length scales and all that to be scaled accordingly, but certain things need to be similar. So in terms of kinematic similarity or forces on models should be similar. All right. All right. So let's see how we do that. Okay. So example. I think they normally do this pipe flow example. Wait, close this one. I don't need this one anymore. Okay. So this example, all right, you need a pressure drop per unit length. Okay, that's your output. That one you cannot control. All right. So normally the analysis do like this. Okay. So first you look at your you group all your parameters. All right. So in this case, delta P per unit length. This is actually the output. All right. The input, so you can put as a function of, all right, what else? Diameter rho mu v. Diameter rho mu v. Right? So this is pipe flow. This is the diameter of the pipe. Rho is the density of the fluid in the pipe. Mu is the dynamic viscosity. V is the velocity. Right? These are the input you can control. All right? You can choose the pipe, you can choose the fluid, which then this pair. You can also change the flow rate or the velocity. Okay, so you control this input, this is the output. Okay, now, so for a particular problem, this part is the most crucial, because if you miss out things, then you can get some sort of random. You will have some sort of random output because they are missing parameters here, which you did not put, you did not control. All right. So and then you can see, hey, hang on, why my output? If I do this, I put the same input. Today I get one output. Tomorrow I get different output because maybe that parameter that you did not include is changing. Does that make sense? Okay, so this part is crucial in making sure you got all the parameters, the input and the output. All right. In this case, simple, one output. But some cases there may be more than one output. All right. Like for pump, the output could be the pressure rise across the pump. It could be the efficiency of the pump. We cannot control. It could be the power required to drive the pump. We cannot control. We can control the pump speed, but power to achieve that speed, we cannot control. All right, so there could be multiple output. All right, but in this case, one output. All right. After that, what's the next step? Next step. All right. Okay, next step is, all right, if we didn't, here, this part here, I explain a little bit. If we didn't have a tool, we would have, just for this problem alone, we will have at least 4 or 5 different charts. Okay? If you have no tool, because we have such a simple problem, we have 4 input. All right? So you need a chart for how all these 4 parameters change. All right? Okay, for example, if we keep diameter, density, and mu constant, this is one set, and we vary the velocity and then measure pressure drop, we get a graph. If we do the same, but vary the diameter, keep the other 3 constant, and get another graph, and so on. So there's this alone, okay, can generate a whole phone book of data. All right, if you just do it naively like this. Does that make sense? That's just these 4 parameters. If you are to try to have a all-encompassing system, all right, or predictive tool, okay, that take in these 4 parameters and give you the output, there's so many possible combinations and so many possible values. Does that make sense? All right? Make sense or not? Okay? You can keep 1 fixed, vary the other 3. Sorry, keep 3 fixed, vary 1, keep 3 fixed, vary 1, and so on. You have a lot of different combinations of graphs. So what we want to do is simplify it. Okay? Alright. Alright, so okay. So I won't talk too long about the story there. Alright. So the first step is normally to identify the number of variables. Number of basic dimensions, sorry. Okay? So this is the dimensional analysis. Okay? So for each of them, all right, let's look at what the basic dimensions are. For velocity, what is it? Is it length over time, isn't it? Okay? Mu? What is mu? Can you remember or not? That's dynamic viscosity. What's the dimensions? You cannot remember, then have to do this way. Shear stress is equal to mu du over dy. Shear stress is force per unit area. Force is mass times acceleration. Divide by area, length squared. Alright. Force divided by unit area. Force is MA. Okay. Is equal to dimensions of mu. Du, that's length over time over length. Okay. So it's actually just 1 over time. Alright. So this, so dimensions of mu is equal to this one cancel off with this one. This one cancel off with this one. M over LT. Correct or not? Looks alright? Okay. So M over LT. Dimensions of this one is mass. Mass over volume. Is that correct? Kilograms per meter cube. This one length. Pressure. Pressure same as this one, force, shear stress. So it's actually M over L squared divided by L. LT squared, that's a force, divided by L is equal to M over L squared T squared. M over L squared T squared. Is that correct or not? M L over T squared divided by L. So it's L squared M L T squared divided by T. Okay? I think so. Is it correct or not? This is pressure, which is force per unit area. Force is MA. Okay? Correct. Mass and acceleration. Alright? Divide by L squared. Correct? Okay. Anyone disagree or not? Oh, so L squared. So this one becomes L cube. Right? Force is equal to MA, which is equal to M L over T squared. Pressure is equal to force over area, which is equal to M L over T squared divided by L squared. Alright, so it should be equal, so cancel out 1. M over L T squared. That's force. Force per unit length. Sorry, that's pressure. Pressure per unit, no lah, pressure per unit length lah, L. Okay? Pressure per unit length. Pressure drop per meter of pipe. Alright? So in 1 meter of pipe, what sort of pressure drop you get? Okay, that's the unit there. Alright, so looking at this, there are 3 basic dimensions. Correct or not? Alright? Are there 3 basic dimensions or not? Well, we can count them out. M, L, and T. Alright? There are 3 basic dimensions. Alright? No more, no less. In this unit, normally 3 only. Sometimes, very rare 2, but normally 3 only. Alright? You can have 4th one like temperature. Alright? Temperature could be in there. And other parameters. Okay? But in this unit, only 3. Alright? Alright, we have 1, 2, 3, 4, 5. 5 parameters. Okay? Alright, and therefore, the theorem, alright, okay, this is Buckingham pi theorem. I don't know why it's called Buckingham pi theorem. You can read up the history in your textbook. Alright, states that number number of dimensionless group equals to, alright, number of dimensionless group equals to number of parameters, alright, input and output parameters included, minus subtract number of basic dimensions. Okay, so basically number of dimensions group in this case will be 5 minus 3, so we should expect 2 dimensionless group. Okay or not? Alright, so we have 5, everybody can count 5 or not? 1, 2, 3, 4, 5. Input output parameter also counted. Okay, so with 2 dimensionless groups, our life will be very easy. You only need to control one input parameter, you'll get one output parameter. Alright, so this has really simplified this problem a lot. Alright. Okay, and also with this, alright. Okay, so next step, next step, we need to choose, if you have 3 basic dimensions, choose repeating variables. Alright, in this case, we have 3 basic dimensions. We need to choose number of repeating variables or parameters, you want to call them. Number of repeating variables equals number of basic dimensions. Okay? Number of repeating variables. So in this case, we have 3 basic dimensions. We need 3 repeating variables. Alright, these repeating variables, later you see, they repeat themselves. They will appear in each dimensionless group. Alright? And in the choice can be arbitrary. Alright, but there are few rules for the choice. Alright? Choice. Alright? Normally we choose from the input parameters. Alright? Don't go choose the output parameter. The output parameter all over the place, but you don't know the output yet. How to find? Okay? So normally choose input parameters. Okay, don't choose the output one. Alright? And there are 2 rules. Among the 3 chosen must contain all basic dimensions. Okay, this is rule number 1. Rule. Okay, let's see. Alright, among the 3 chosen, they must contain all among the 3 alright. Doesn't mean each one must contain M, L and T. Alright, but if you choose this, this and this, M must appear in at least one of the 3, L must appear in at least one of the 3, and T must, not T, K, not TK, M, L, T. T is time. T must appear in at least one of the 3. Does that make sense? So, in other words, let's see. If I choose, in this case, alright, any choice also can, isn't it? Let's say if I choose rho, mu, and D, alright, rho, mu, and D, M got, more than one, no problem. L got, all 3 also got, T got, okay. Alright now. If you choose rho, mu, and V, M got, L got, T also got. Yeah. Alright? Is that okay? So in this case, this simple case, any choice also can. Alright? Rule number 2 is cannot form a dimensionless group on its own. Okay? And I'll talk about forming dimensionless group in a short while. Alright? We'll come back to rule number 2, but I believe we don't violate them. Okay? So how to form dimensionless group? Let's say first you need to choose 3. Alright? Depending on the problem, alright, in this unit, sometimes you can have different choices one. You can still get the right answer. Alright? Even exam, don't panic. Your answer doesn't need to be exact as the same. In this case, as I said, I can choose rho D rho mu, D rho V also can. Rho mu V also can. Alright? Got more than one choice. Okay? So which one you want to choose? Normally, okay? Normally, choose, if they appear, you choose rho, V and D. That's a common fella. Alright? That one is, if they're there, if they're not there, you cannot choose them. Okay, but if they're there in the input parameter, you don't normally choose them. Alright? That's the norm. But if you want to go against the norm, it's okay. Alright? You can be unique. It's okay. Alright? Yeah, that's why not many people like come my 7 o'clock class. Even the men, they scared of going home at night. There's some weirdos out there. Okay. Alright. Don't need to. Okay. Alright, so any questions here? Alright. So I try not to run too many classes up to 7 o'clock. Alright. So, no, today not under 7 o'clock. The last Monday to Wednesday was up to 7 o'clock. The tutorial replacement. Alright. Okay. So, this one we finish this problem, then we finish up. Okay? Hopefully we finish before 6. A few minutes after 6, but I expect to finish around there. Alright. So, I chose rho, V and D. Okay? So, what I say, how to form a dimensionless group is like this. Okay? So, we take these repeating variables, and when we take this, alright, firstly, our one is what? Delta P over L is a function of rho, V, D, mu. We cannot think of anything else for now. So that's it. Okay, we take these fellas out. Okay, so there's only left this one and this one. Okay, this will be one dimensionless group, pi 1, and this one will be another one, pi 2. Okay, how do you form pi 1? How do you form pi 1 is like this. Okay, one dimensionless group is equal to delta P over L divided by rho to the A, V to the B, D to the C. We find A, B, and C. Alright, they are normally integers. We find the integers A, B, and C so that this term is dimensionless. Okay or not? Alright? Or we find this term the other way also can. In other words, rho to the A, B, C, D, V to the E, rho V, D to the F over mu. Also can. Because they are dimensionless. A dimensionless number, if you invert it, is it dimensionless or not? Alright, so it can be either way one. Alright? So again, there is no unique answer, but there are a few standard forms. We'll talk about the standard ones next week, but these are the my choice. Okay? Alright. So how to form? First, okay, let's do this one first. Okay? So actually this one, pi 1 is equal to, just replace it with, replace each variable with its dimensions, alright, and then solve for A, B, and C. That's how we do it. Delta P over L is one, M over L squared T squared, M over L squared T squared, divided by rho is M over L cubed to the power A, V is L over T to the power B, D is L to the power C. Okay? And we say this one is the dimensions of this whole thing is equal to 1. No dimensions. Is that okay or not? So for the M, so we have, for that, basically this whole thing must be equal to M to the power 0, L to the power 0, T to the power 0. Okay or not? Alright, that's dimensionless. Alright, so for M to the power 0, okay, for the M equation, on top I have 1. 1 minus A equals to 0. Is that okay? So M to the power 1 divided by M to the power A, divide is equal to 1. Alright, it's equal to 0. Or in other words, here I'll have, alright, I will simplify this for those who M to the power 1 minus A. Is that correct or not? Alright, L I have minus 2 plus 3A minus B. Again, I repeat, minus 2 plus 3A minus B. Right? Minus 2 because the top fella is minus 2. Bottom fella, L to power 3A, but is a denominator, so actually a denominator of a denominator becomes a, what's the top fella called? Numerator. Alright, 3. L to the power B is a denominator, that's why it's minus B. Is that okay? And T to the power here, minus 2, here, minus B, but since it's a denominator of a denominator, it becomes a plus B, is equal to M, oh, there's also a minus C. Okay, M to the naught, L to the naught, T to the naught. Okay or not? M, that on top there, 1. M to the power 1 on the top. M to the power A to the bottom. Okay, don't worry about that first. Worry about this one first. Can you understand this one or not? Can you understand this one or not? Who cannot understand? Alright. Okay, it's just this here, I just group them together. Alright, group the M's together, group the L's together, group the T's together. Is that okay? Alright. Some are okay, some are still. Alright. The mass, length, and time are distinct. Alright. Mass cannot turn into length, length cannot turn into time. So although they are together like this, we have to separate them. Alright? And for each of them to be dimensionless, alright? For each of them to be dimensionless, each of these creatures must equal to 0. So we have 3 unknown, A, B, and C. We have 3 equations. 3 unknown, 3 equations can solve or not? Normally can. Let's try. Alright, so first one for the m, here m to the power 1 minus a, we need to be 0. Alright, that one, a equals to 1 already. Alright, equation for the t, do the easy one first, then we come to this one. Okay, for the t, minus 2 plus b equals to 0. B equals to 2. Okay or not? For the L, minus 2 plus 3a minus b minus c equals to 0. So, minus 2, 3a plus 3 minus b minus 2 minus c equals to 0. C equals to 3 minus 4 minus 1. Is that correct? 3 minus 4. So negative C, I move the negative C to the other side. Okay, so that's the source. Okay or not? Who still not okay? Alright? Who still think I cheated them in this step here? Alright? So, if I didn't cheat you here, then it's just solving this one, it's nothing there. So, after that, we take this combination and put back. Pi 1 is equal to delta P over L. Alright, roll to the A now is 1. Roll to the A, 1 is 1. V to the B, V squared. D to the C. C is actually up here. C to the power minus 1. You can put here L, D to the minus 1, or you can put delta P on L, D multiply it, rho V squared. Okay? So this parameter is dimensionless. Alright? Is that okay? This parameter is dimensionless. Your long weekend, you can go home and check. Alright? You go prove to yourself. Make sure you're happy. Alright? Make sure you believe. Yeah. Don't be skeptical about this one. There's a lot of other things to be skeptical about, but not this one. Okay? Alright? Any questions so far? So we do the next one. This one? This one, it would... No, you don't need to prove. That's part of... What the question in front here is, why do we want this to be dimensionless? The answer is, this tool, by doing it this way, it's number one, it simplifies it's one way of reducing the number of variables. Alright? And number two, it also removes the ambiguity of using different units and so on. Okay? Alright? Ambiguity of the units, number one. And number two, this tool allows you to reduce the number of variables, all right, or the number of parameters from 5 to 2. Okay, we're currently reduced by 3 here. All right. Okay. So let's see. You okay so far? All right. So the next one. Alright, if you understand the first one, then the next one is very easy. If you don't, then this, at least you get another chance to look at it happening. Alright, I say it's rho to the A, B, C, D, rho V, D, E, rho V, D to the D, E, F over mu. Alright, up, down is up to you. You can choose. I choose it this way because normally it's this way. Alright, but you want to choose it down, it's not wrong. Okay? Just a bit different. Alright. Okay. Rho is what? Yeah. Okay. Rho is mass. Therefore, alright. Rho is mass per length cube to the D. V is length over time to the E. Dimensions, this is length to the F over mu is what? What did I say was? M over LT, is it? Okay, I think so. M over LT. Okay? And this supposedly is equal to M to the naught, L to the naught, T to the naught. Right? Dimensionless. Okay? So if you want to have the intermediate step, can M to the D minus 1, L to the minus 3D plus E plus F minus 1 becomes plus 1. Alright? ML T minus E plus 1 equals to M to the naught, L to the naught, T to the naught. Alright? E is T to invert here is E. The denominator becomes a numerator. Alright? So again, 3 equations, 3 unknown. Alright? So do the easy one first. D minus 1 equals to 0. D equals to 1. E minus E plus 1 equals to 0. E equals to 1. This is actually for the M term. This is for the T term. And then for the L, normally the most difficult. Minus 3D plus E plus F plus 1 equals to 0. So minus 3D is D is 1. Minus 3 plus E is 1. Plus 1 plus F plus 1 equals to 0. F equals to 1. So put back. So D equals to 1, E equals to 1, F. Put back. Pi 2 is equal to rho V D over mu. Alright? And this is actually Reynolds number. Alright? Yep. This number will appear quite a number of times. Alright? That's why those numbers that appear quite a number of times, they give it a name. The name after a famous person. I'll talk about him later. He worked in University of Manchester. He did a famous experiment, and the experiment rig is still sitting there in the university. Okay? So, come down, not finished yet. Alright? Alright? No. Okay, so pi 1 equals to some other function, pi 2. Okay? Therefore, delta P over L multiplied by D multiplied by rho and V. Is that correct? That's pi 1, isn't it? Is equal to some function of rho V D over mu. Okay? So, alright. Okay, so basically for this problem, if we captured all our variables, alright, in the parameter at the start, if we missed out, then we get some strange behavior. But if we captured everything correctly at the start, because this picture is really only dependent on the 5 parameters that 4 other parameters, for the input parameters. If that is true, then for every time, if we fix this, we will get the same this one. Alright? There will be only one graph you need to plot. Okay, rather than so many graphs. That graph is, okay, you only need to plot one graph. Alright? All your data should collapse on it. If you plot input parameter rho V D over mu, output parameter delta P over L, D over rho V, alright, you get a curve, and I don't know how to shape a curve. All the data should fit here. Okay? If you do another experiment in another country with a different rig, a different person doing it, his data also should be here. Okay? If the data end up like that, I mean something wrong. Either experiment not carried out correctly, or we have some missing input parameter at the start there. Maybe it's also dependent on the color of the pipe. I don't know. Okay? Normally no lah, but that one we didn't count. So if you get a blue pipe, you get a different result. You get a red pipe, you get a different result. If that is the case, then we didn't count for that. Alright? But if not, this shouldn't happen. Alright? One last thing, hey, 5 more minutes lah. Okay? Remember I told you rule number 2, now that we know how to form dimensionless groups, I illustrate to you rule number 2 before we finish. Okay? You know I have to go and start the rule number 2 next time. Alright? Okay? Cannot form a dimensionless group on its own. Let's illustrate rule number 2. Rule number 2. Okay? Don't worry lah, 5-10 minutes. Outside still quite early, before 7. Should be able to safely go home. More or less. Alright. So in other words, rho VD on its own tried to form a dimensionless group. So I don't know, call this one to power X to power Y. Okay? Alright. So rho is M over L cube. V is L over T to the power X. D is L to the power Y equals to M to the naught, L to the naught, T to the naught. Okay? If we can find value for X and Y, means there's a problem. Okay? Let's see. If cannot, then it's okay. Alright, M. Cannot already. Alright? Impossible already. So, maybe don't put it here. Go V, B, put the X and the Y here. Put the X and the Y here. Okay. So here is M to the X, T to the minus Y, L to the minus 3X plus Y plus 1. Okay? Let's see whether you can solve or not. Right? Looks difficult. Alright? From here you can see for the M term, X is equal to 0. For the Y term, P, Y or minus Y equals to 0. Therefore, Y equals to 0. So it doesn't matter this one already lah. Alright? Cannot form. Right? You just get zeros. Alright? So, impossible. Impossible to form dimensionless group. So, okay. Rho VD passes rule number 2. Okay? So, with that, we finish. We continue next week. Have a good long weekend. Alright? Hopefully you it's not that late. You should be quite safe to go back to your car or however you transport back. Okay. Huh? You can give also yeah, here Z. Normally we don't give to one of them one. Huh? I mean here earlier.
If like there are 4 variables, I can give 3 of them, but then the other one
because it's all relative. Alright, if you give the other one a value, alright, you won't be able to. You have like an extra. In other words, you can scale.
mean that it's better to calculate out.
In other words, you can give it, but you get an arbitrary scaling. In other words, if this is a dimensional variable, this whole thing squared is a dimensional variable. This whole thing cube is a dimensional variable.
If
So
I have 4 variables, I give 3 of them.
yeah,
then I left one out.
yeah, you leave one out, and then that one would be 1 relative to this one relative to this is dimensionless. In other words, if you give it 2, here all will just go to 2, and it's all with dimensionless.
And then this pi 1, right? This pi 1 is actually what we want to look for. This constant comes from mu, right? This is for mu. This is for
No, this is for mu.
this is for
Wait,
mu.
yeah. So